Hello, this is Ian Parberry. I'm here to talk to you about my Computing Foundations 1 class. I'm going to be teaching this section, Section 1. My colleague Dr. Schneider is going to be teaching Section 2. We're going to try to keep in sync as much as we can given the calendar changes between the two sections. Here we are. So why are you taking this class? Yeah, I know, because you have to. Really, you're taking this class so you won't waste time reinventing the wheel every time you program something. There's a vast amount of stuff out there invented and developed by other people that you can hook into. You know what they say, of course, when you have a hammer, everything looks like a nail. So what are the nails and hammers here? The hammer, in this case, is a collection of standard algorithms and data structures. But how do we apply these to the kind of problems that occur in an everyday programmer's life? That is, how do we make everything look like a nail so we can hammer it? The answer is abstraction. The standard algorithms and data structures are described using abstract objects. A lot of the tasks that you're likely to run into as a programmer can be mapped directly into these abstractions, and therefore you can make use of those standard algorithms and data structures that have been pre-programmed for you without having to do much work. So what lies ahead? In this class you're going to be learning how to integrate theory and practice. Theory means some math and some abstraction. This is not easy. Computer science students tend to have a problem with this. But this is the start of your journey on the road to becoming a master programmer. A master programmer does not reinvent the wheel. Let's look at a quick example, that of exam scheduling. The problem is we want to schedule final exams for UNT, let's say, so that if two classes have their exams in the same time slot, then no student is taking both classes. So we don't want to require a student to be in two places at the same time. The abstraction we're going to use is a graph. Now a graph consists of a bunch of nodes, which we draw as circles, connected by lines, which we call edges. So in this graph, the nodes will represent classes, so we'll have a circle for each class, and we draw a line between those circles, or a line between every pair of circles that has a common student. So the nodes represent classes, the edges represent the existence of common students. So what we want to do here is find a maximal independent set. Now, an independent set in a graph is a bunch of vertices that don't have any edges. So an independent set then in our abstraction represents a set of classes that don't have common students. Therefore, we can schedule their exam at the same time. Remove that independent set and repeat. Yeah, I forgot the word maximal. Of course, each time we want the independent set that we remove and schedule to be as big as we can. Maximal means we can't add any more nodes to it without violating the independent set property. So here's an example. Suppose we have 5 classes to schedule: English, Math, Computer Science, Economics, and Physics. And we'll represent each by a circle, those green circles you see there. Now, let's say we have 3 students, Anne, Bill, and Chris. Anne is in Computer Science and Economics. Bill is in English, Math, and Computer Science. Chris is in Computer Science and Physics. So you see, for example, we can't schedule Computer Science and Physics at the same time because Chris is in both classes. Alright, so we make a course conflict graph. As I've said, we have those 5 nodes, one for each class, and we draw an edge or a line between 2 classes when there's a common student, or at least one common student. I put one of the names here if there are many. Bill. So because of Bill, we can't have English and Math together. Because of Chris, we can't have Computer Science and Physics together. Okay, so definitions then. Independent set is a set of nodes that have no edges to other nodes in the set. A maximal independent set is one to which no additional node can be added without violating that independent set property. So here's a possible schedule. Notice over here, English, economics, and physics form an independent set. There are no edges between nodes in that red set there. So we could schedule those exams at the same time. They have no common student. So let's go ahead and schedule English, economics, and physics. Next, if we take computer science, we can't put math at the same time. There's an edge. So computer science and then math. We need 3 time slots then to schedule our exams. So we send this list off to the administration. There's another possible schedule. Notice also that math, physics, and economics form an independent set. So we could schedule math, economics, and physics together, and then computer science and English separately. Not at the same time, of course, because they have an edge between them, and we'll get this schedule then. 3 time slots still. Both using maximal independent sets. Both are viable solutions. So does this method always produce a feasible solution? Yeah. Does it always produce the best one, the one with the smallest number of slots? Turns out it doesn't. And there are some fairly deep mathematical reasons why it doesn't. This is an example of what's called an NP-hard problem, which you'll get to see later in the algorithms class probably. Can this abstraction cause any practical problems? I can't think of any. Can you implement a solution to this problem using techniques you already know? Yeah, absolutely. You should be able to do that. Implementation 1 is, say, using a 2-dimensional array, an instance matrix. I hope you've seen these before in your earlier prerequisite classes. So we list the nodes along here and down here. In the middle, we write a 1 if there's an edge between here nodes 1 and 0. Yes, there's an edge here, so put a 1 there. We'll put 1s down the diagonal too. 0s if there's no edge. So for example, here between nodes 4 and 3, there's no edge. Notice this array is symmetric about the diagonal, so in practice we'd only store half of it. So does this method always work? Yeah. Is it efficient, or could there be a faster way to implement it? Yeah, finding the next node to add to your independent sets to make it more maximal. There could be faster ways than just looking at the next node each time. How can this algorithm be improved? That actually is an open problem. Alright, so a data model is an abstraction to describe problems. Examples include things like trees, lists, sets, relations, finite automata, grammars, logic. There are static and dynamic aspects to this. They're used in type systems and operations. Some data models are provided in programming languages. C++ has some fairly basic things like integers, floating point numbers, structures, pointers, etc., which are actually building blocks that we can build more complicated data models from, as we'll see later in this class. So a data structure then represents the data models in a programming language. They're not usually explicitly part of the language. As I said, we build them up from smaller parts. And they're not the same for all languages, because the data models supported by programming languages vary from language to language. An algorithm, as I hope you know already, is a sequence of instructions to solve a problem. So for example, a recipe in a cookbook is an algorithm for baking a cake. Algorithms that describe code are often written down in what's called pseudocode. That is something that looks kind of like code, but with all the details taken out, because we're human beings and we can figure out what's going on. Some examples of standard algorithms are sorting, searching, scheduling. Important properties of these algorithms are simplicity, running time. Simplicity means they're easy to understand, easy for other programmers to modify. Running time is, how fast they run, given the amount of data you want to apply them to. So, data models of programming languages. Think of data being stored in boxes. Boxes have types, names, and contain data objects. So if in C++ I said int x equals 5, we've got a box that has an integer in it, which we call x, and it currently contains the data object 5. There are static data types like integers, characters, and arrays. There are dynamic things like arithmetic operations, dereferencing, accessing operations, etc., which can actually change data. There's a data model of system software that I'm sure you're familiar with, data stored in files, organized in directories, and that's the Unix file system, much simplified. Now, data model of system software on real computers, processes, executions of programs, and can be concatenated in Unix. You'll be using Unix in this class. For example, you can take ps-u username, pipe it into grep gnome, into head -2, and I hope you can tell me what the result of that is going to be. Think. Well, the head -2 is 2 lines of grep gnome is all lines containing the word gnome. ps-u username is all the processes associated with that username. So you would find the top two processes of that username using the program gnome. Software applications have their own data models. For example, a text editor works on text strings. It may have data units in terms of lines, or words, or groups of text. Editing operations include insertion, deletion. You may also want to do a search. Alright, now, Dr. Snyder tells me that people have a lot of trouble with decimal and binary numbers. Now, binary numbers are what goes on inside the computer, so it's important that you understand this concept. So, let's start with a simple example. How do you convert the number 12 to base 10, that is normal everyday 12 that we're used to its binary representation? Alright, let's figure it out here, this complicated diagram. If we say 12 divided by 2 is 6 remainder 0. Cool, take that 6. 6 divided by 2 is 3 remainder 0. Cool, take the 3 over here. 3 divided by 2 is 1 remainder 1. Yeah, 1 times 2 plus 1 is 3. And 1 divided by 2 is 0. That means we're done. Remainder 1. If we take these remainders here and read them backwards, 1, 1, 0, 0, that is the binary representation of 12. Let's think a second. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 8 plus 4 is 12. Yeah, cool. We can use the same technique to convert to the tertiary system, not binary, tertiary, using 1s and 2s. Here we go, let's convert, it's 14, not 13. 14 divided by 3 is 4, 3 4s are 12, remainder 2. Okie dokie, take the 4 over here. 4 divided by 3 is 1, remainder 1, take the 1 over here. 1 divided by 3 is 0, we're done. Remainder 1, backwards 1, 1, 2. So 12 to base 10 is 1, 1, 2 to base 3. So converting between number systems. How do you convert binary to decimal, for instance? Let's not do all that diagrammatic work there. That process back on the previous 2 slides was pretty easy. We can, once we get the hang of it, do it a lot quicker. Alright, take the powers of 2, and if you're going to be dealing with computers, powers of 2 will after a while become second nature to you. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2040. Those should spring immediately to your mind. Okay. So multiply each digit by the binary number. So let's see, 1011. 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 is 8 plus 0 plus 2 plus 1 equals 11, and that's your base 10 answer. 1011 in binary is 11 in base 10. Hang on a sec. Is this the same as the previous slide? Oh boy. Okay. 1100 is 12 to base 10. Another example. In base 5, excuse me, I need some coffee here. Good coffee. How do you convert 1010 to base 5 to the decimal system? Okay, here's something new. Not binary to base 5. Same idea. Instead of 2, we put 5. So over here, 5 to the 0, 5 to the 1, 5 squared, 5 cubed. They're not so familiar to us, but the 1, 5, 25, 125. Multiply each of these by the corresponding digit. 1, 0, 1, 0. 1 times 125, 0 times 25. 1 times 5, 0 times 1. Add those up, and we get 130 to base 10. Alright, so now you're familiar with binary representation. You learned in elementary school how to add decimal numbers. We'll call this the ripple carry algorithm. And here's how it worked. We go 6 plus 9 is 15. Put down the 5 at the bottom, carry 1 at the top. So the resulting digit is down here in blue. The carry is up here in orange. 9 plus 6 is 5 carry 1. Alright, then we do the next column. 5 plus 2 plus 1, 5, 6, 7, 8 is 8 carry 0. There we go, 8 carry 0. Now the last column over here, 8 plus 4 plus 0 is 12. Put down a 2, carry 1, there's nowhere for the carry to go, so it falls down here. There we go. Answer is 1285. Easy, elementary school stuff. Now we can do that in binary too. Let's add the binary numbers 101 plus 111 without converting to base 10 and back again. That's cheating, but you could do that to check your work. It's real easy. We do the same thing except, oh, it's in binary. 1 plus 1 is what? 1 plus 1 is 1, 0. Put down the 0, carry the 1. Here we go. Put down the 0, carry 1. In the second column over here, 1 plus 0 plus 1 is 1, 0. Same thing. Put down the 0, carry the 1. 1 plus 1 plus 1 is 1, 1. Put down the 1, carry the 1, which falls over here. And the answer is 1100 in binary. Alright. Now, let's try to build a circuit for doing addition. We have some basic units that engineers can build for us, like AND gates. Let's use current flowing through a wire to be a 1, current not flowing to be 0. Then we can make an AND gate pretty easily that takes in two values x and y, output z, which is a 1 if and only if the two inputs is are 1. That is, the AND of both inputs is 1. That's an AND gate. Over here on the right we've got a truth table here. When we get 0, 0, 0, 1 or 1, 0 on these two input wires, we output 0. We only output 1 when x and y are both 1, that's why it's an AND gate. We can build a 1-bit adder then, taking in x and y and a carry bit c. We can output the sum bit z and the carry out bit d out of AND, and yeah, we also need OR gates pretty easily. Alright, so once we've built that, given, here we are, given x and y, if x and y is 0, carry is 0, right? If x and y are, if x and y and the carry in are 0, the carry out is 0, and z is 0, etc. Do this for all of the possible entries, and you will see how the outputs here relate to the inputs. Once you've got this little addition unit, you can chain a bunch of them together and get what's called a rippled carry adder by taking the carry out of one and putting it into the carry into the other to implement the addition algorithm we used earlier. Alright, so that's addition binary subtraction. We're going to cheat and use the 2's complement. That's another thing computer scientists like to do. When you've got a hammer, everything looks like a nail. Subtraction looks like addition. To subtract, let's say you want to do 5 minus 4 in decimal, that is in binary 101 minus 100 in base 2. Okay, we start by taking the 1's complement of the negative term, the minus 100. 1's complement means flip each bit, so 100. Over here, flip each bit, becomes 0, 1, 1. You add this bit, 101, to the 1's complement of this, so add the 1's complement, and if there's a carry out, add it in to the result. Carry out meaning a carry out of the 3 bits, a remaining carry. That nasty carry we had to float down to the bottom line earlier. Okay, so let's try 101 minus 100. As we said, flip the bits and it becomes addition. 1 plus 1 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. 1 plus 1 plus 0 is 0, carry 1. That last carry we don't put up next to the zeros, we put down at the bottom and add it to 0, 0, 0. And the answer is 1. Yeah, of course. When I take 101 and subtract 100 from it, of course I get left with 1. That's obvious. Now, decimal subtraction can be done in 9's complement too. They didn't teach you this in elementary school, but it works just as well. So 9's complement, let's do 102 minus 52. And note I've been a bit sneaky here. I've put a 0 in. Yeah, we've got to make sure these have the same length for this to work, but no worries, just stick a 0 there. 9's complement of this term is, okay, 9, 4, 7. 9's complement means 9 minus this thing. 9 minus 0, 9 minus 5, 9 minus 2. 9, 4, 7. You add 102 then to the 9's complement of that. If there's a carry out, add it to the result, like before. So let's try it. 102 minus 52 becomes, taking the 9's complement, 102 plus 947. 7 plus 2 is 9, carry 0. 0 plus 0 plus 4 is 4, carry 0. 9 plus 1 plus 0 is 10. And remember, the carry doesn't go next to the 49. We take it down. Here we go. 049, the carry at the bottom. 49 plus 1 is 50. So that's the result of the subtraction. Look back and see if we're right. Alright, that's one example of abstraction. We have another abstraction we'll go into in more detail later. Lists. Lists enumerate elements of a specific data type, like lists of integers, lists of strings. Concept of list then is an abstraction. We're going to look at some examples of list implementations, data structures, that is, some linked lists, some arrays, etc. Some languages, of course, have lists as part of their data model, like Lisp and Prolog, but we're not so lucky here. We're going to have to do it ourselves in C++. So in a linked list, we would represent 5, 1, 3, 12 as the linked list where we have a structure over here, a C-type struct, we'll call it, cell, with an element and a pointer to the next structure. So 5 has a pointer to this unit containing a 1, has a pointer to this unit containing a 3, has a pointer to this unit containing a 12. Alright, so the C data model is an example of a piece of C code. Include standard io.h. Here's my main. Set num to 0. while it's not end of file ++ num printf that number. Yeah, that's adding the number of finding out the number of characters in the input. C static types include characters, integers, floating point numbers, enumerated types, and we can form new types with arrays, structures, unions, and pointers. The C static type system works like this. We can declare here type 1 being an array of 10 integers, type 2 being a pointer to type 1, etc., and build up structures in this way. We end up with a complicated picture like this. Now, while computers are using binary representations, we have this abstract concept in mind of where we have an array here where element 0 has two fields. The first field has number 3, the second field is a pointer to a bunch of stuff. We have dynamic type systems. In C we have malloc and free. In C++, as we'll see in a couple of lectures, we have new and delete. We can access and modify objects, for example, accessing arrays here, array A sub I, for instance. We can combine object values using the usual kind of operators you've worked with before: arithmetic, logical, comparisons, some assignments, some coercion, typecasting, that is, operators. Alright, now let me touch briefly on principles of software design. How are people designing software using these abstractions? There's the waterfall method, the iterative method, and rapid prototyping. Waterfall method is largely discredited. Old books continue to use it, but in practice it just doesn't work because people aren't as logical as the waterfall method assumes. So in the waterfall method, we start off with the specification. We specify what we want to do. We go through design, implementation, verification, and maintenance. That just says, okay, figure out what you want, design how you're going to do it, implement it in code, check to see if it's right, release it, and then all you need to do is maintain it. Well, things aren't always as easy as that. For one thing, the customer doesn't always know what he or she wants. This is the iterative method, in which we keep iterating until we're happy with the result. We start, we specify, we design, we implement, we verify, and then we go around the loop again. Once we figure that out, we keep going around, adjusting the specification, design, and implementation until we're happy. Then we release and maintain. Prototyping then breaks this up into, let's say the company that's hired your company to do this doesn't really know what they want. They know kind of what they want, but they're not techies. They're not like us. They don't know how to program, so they don't know what's quite possible. So you take their vague ideas and show them what can be done. You start, you go through a design phase, you implement, test, evaluate, and go around this loop enough times until they're happy, and then you implement the full thing, send it to quality assurance, test it, and then you're done. Right, so in summary, I've talked about problems, models, solutions, data models, data structures, algorithms, and for this, I would like you to read the textbook, Chapter 1. Thank you. Bye-bye.